back at it again. So we have finished chapter 17 at this point, which means we're going to spend the next few videos just reviewing this content on sampling distributions. So remember, we've dealt with proportion sampling distributions and quantitative data sampling distributions as well. So we're going to look through how you're actually going to use this for quite a few different examples of problems. For the first two videos on the review portion of this chapter, I'm just going to go through some book questions, all right? And then for the last video of review for this one, we're just going to look through an extended response question. Now, what type of work are you going to be doing for this? Well, at the end, after we go through all three videos, I'm going to release a extended response type question or a few of them for you guys to work on, just because we really need to start getting in the mindset of like open response questions, since that is the only thing the AP test is going to be covering now. So we're going to have to practice that. But otherwise, what work should you be doing this week? We are going to be going through book work, and I'm going to be explaining the questions step by step. What I would suggest you do is at the beginning of each question, pause the video and do it on your own first.
It's impossible.
And then go ahead and see, hit play, finish the recording, and see what I said the answer should have been. But you should be attempting these on your own first. You've seen all the content, you've learned all the material. See if you can do it on your own first, and then go ahead and hit play and see me go through it. So again, for this entire group of 3 videos we're doing review, you should be doing the questions on your own. So the moment the question pops up, hit pause, go ahead and attempt the question on your own. Then when you're either feel like you got the answer and you're ready to go, then go ahead and hit play and see if your response matches my response. All right. So that's how this is going to work, and we're going to jump right into the book work. All right. So this one says, when they send out their fundraising letter, a philanthropic organization typically gets a return of about 5% of their people on their mailing list. To see what response rate might be for future appeals, they did a simulation using sample sizes of 20, 50, 100, and 200. For each sample size, they simulated 1,000 mailings with a success rate of P equals 0.05, or 5%, and constructed the histogram of 1,000 sample proportions. Explain how these 4 histograms demonstrate what the central limit theorem says about sampling distribution model for the sample proportions. Be sure to talk about shape, center, and spread. Shape, center, and spread. So don't let this all this mumbo jumbo get in the way. Let's go through and see what's actually important here, okay? What they're saying is that a company is going to take a bunch of samples over and over and over. Now, the sample size is going to be different for each graph. For example, the sample size here is 20, sample size here is 50, sample size is 100, and sample size is 200. Now, when it talks about the 1,000, what it's saying is it's going to use a computer program to draw 1,000 samples of size 20. So that means that it's going to hypothetically send out all of these letters, all right, to 20 people, and then it's going to find out the proportion of those 20 that respond, and then it's going to do that 1,000 times, and it's going to make a histogram of the responses that pop out, okay? So what does the central limit theorem say? Remember, the central limit theorem kind of talks about the idea of if you're taking samples over and over and over again for proportion, we would expect that as long as the conditions are met, that our sampling distribution would have a mean that is focused around the true proportion, so in this case 5%, and it says that the distribution itself should look almost like a normal curve. So if we look through this data, how would this prove the central limit theorem? Well, first off, let's look. What's the major difference between these 4 graphs? Their sample size, all right? So how would the central limit theorem be related to a sample size of 20, 50, 100, and 200? The central limit theorem would be saying that as that sample size is increasing, we should expect this data to get more and more normal, and the mean of that sampling distribution should be closer and closer and closer to the 0.05. So let's talk, walking through this, how we would comment about the shape, center, and spread for each one of these, okay? So starting off, the first one of sample size 20. All right, this guy right here. The sample size of 20 says, let's see, we would define this as being skewed right because it's going down. So this is not normal yet. This is not an approximately normal graph. It's definitely skewed right, with most of the stuff being down here by the 0 to 0.05 range. But the difference here is that we have some answers all the way up to 0.25, which would be quite a distance from the 0.05. So the spread here is actually extremely large in relative to the situation. So our shape turned out being a little bit skewed to the right. Our center is, let's see, if this is 25, that means it's probably 5, 10, 15, 20, 25. So we actually expect the center probably to be somewhere around like right here. So it's actually somewhere between that 5% to 10% mark, all right, which is pretty close to our 5%. But our spread is larger, all right, and the shape is skewed right. So as we move up to a sample size of 50, all right, sample size of 50, you can notice we're starting to drift away from this extreme skewed right. Now, I would still define this slightly skewed right, all right, but you can see down here we're kind of going to be still in that same boat, but it's going to be slightly skewed right because of this curve, all right. But you can notice the spread here no longer goes from 0 to 0.25, it goes from 0 to 0.15. So our spread has gotten much smaller. So our spread now is between 0 to 0.15, which means we're talking about 5, 10, 15, which means the center of this is probably going to be right here around like 0.6, 0.7, because if this is 0.5 right here and that's 0.10, you're talking more around the 0.6, 0.7 range, okay? And we're going towards the normal curve, but not quite there yet, all right? Down here at a sample size of 100, at this point, we are getting pretty close to where we want to be, all right? We're looking at 0.14 for a spread, so we've decreased, not by much, but at least by some. We went from 0.15 to 0.14 for our spread, and you can even that not super special considering the fact that part of that is this one guy that's over here, because you can even see there's a gap. So that means there was a super rare sample that occurred in there that made it to 0.14. But for the most part, we are getting close to our little bell-shaped curve that's a little skinnier than usual because sampling distributions are kind of shoved towards the middle since they're just means. But notice there is still kind of a curve on this side, whereas this one's more of like a slant going down. So what's this saying? It's saying we're at 100 now. Our spread is getting smaller. We're down to 0.14, so that's a little bit more reasonable. Our center looks like it's falling about right here now. All right. Which, if that's the case, if this is 14, I'm going to guess it's going by 2, 4, 6, 8, 10, 12, 14. So coming by twos. So 2, 4, 6. Somewhere right here between the 5 and 6 mark is where we're falling. So we're almost at that 5%. So we would expect our center to be pretty close here. And for our last guy here, we can finally see that the curve's kind of even on both sides here. So this is as close to being approximately normal as we're going to get. So for our sample size of 200, our central limit theorem is in full effect. We are seeing that the middle is, let's see, straight down the middle here. It looks like it's slightly less than 0.06, which means we're probably sitting right at 0.05. It is almost the same amount of curve on both sides, so we're looking at it being approximately normal. We're now only going from about 0.02 up to 10, so we are way smaller spread than we were in the beginning up here, all right? So what is this saying about central limit in general? In general, as we went and progressed through these 4 graphs, you can see that as our sample size increased, we became more and more normal shaped, approximately normal. We became more and more centered at 0.05, which was the true proportion. And we became more and more less spread out. So our spread got smaller and smaller and smaller. So that kind of defines the central limit theorem. Those three things are kind of what the central limit theorem hits. So that's how these four pictures would represent that. Now, obviously, I did a very long-winded version of all of that, and you wouldn't want to write all of that down. But in general, if you were answering this question in words, I think you would want to talk about the fact that you would say, hey, in terms of shape, going from 20 to 50 to 100 to 200, we can see that it gradually shifted from being skewed right to being approximately normal. In terms of center, looking at 20, 50, 100, 200, we went from kind of being all over the place to really honing in our center being exactly at that 0.05. In terms of spread, we had an original spread of 0 to 0.25, and as our sample size increased, we saw that our sampling distribution spread fell down to more between like a 0.02 to 0.10 range. All right. So in general, those three things shifted as we moved our sample size up and up and up. And that's more about what you would have written about, not so much the individual breakdown of each graph that I did for you. All right. Let's go ahead and take a look at the next question. All right, so for this question, it says the same organization with the 0.05 success rate or the 5% success rate, they actually did the exact mean and standard deviation for each situation. So you can see here it has the sample size of 20, what was the actual mean and standard deviation of their little distribution. Here's the one for 50, 100, 200, and so forth. And it gave you the actual mean and standard deviation of those graphs. Then it asks us a few questions to kind of look at here. It says, according to the central limit theorem, what should the theoretical mean and standard deviation be for these samples? Now remember, when we're dealing with proportions, the theoretical mean should be whatever the true proportion was. In this case, the true proportion was our 5% that it tells us, all right? So that means that our theoretical mean should be 0.05. So that's pretty easy. Now, what's not as easy is the standard deviation. If you remember in the notes, we talked about the formula for standard deviation being the square root of P times Q divided by N. Now remember, in this case, what would each of those be? P and Q wouldn't change. P is the probability of success, which is 0.05. Q is 1 minus that, so 0.95. So the 0.05 and 0.95 wouldn't change in that. What would change for each one of these that we did would be the sample size, N, all right? So you can see here I have written out, in order to find each one of these standard deviations in the calculator, I would just hit square root. I'd do 0.05 times 0.95 divided by, and I would just plug in each of these numbers, 20, 50, 100, 200. And I would do it for each of those four and get my answers. Just to kind of save us some time, I went ahead and plugged each of these in. And those are the four answers that we should be getting. So 0.048, 734, 0.030, and so forth, all right? Now, those numbers look daunting, but again, all I did was plug in this formula over here and went ahead and wrote the answers that the calculator gave me right there. So it asks for the theoretical mean and standard deviation for each sample size. We have now done that. The theoretical mean for all of them would have been the same of 0.05, and here would be the list of the standard deviations. For part B, it says how close are those theoretical values to what was observed in these simulations? So notice this first one is off by almost 0.001, all right? Whereas the second one's off by almost 0.0001 and so forth from there. So again, you can see that as the sample size gets larger, that theoretical value gets closer and closer to the actual value. And you can see down here, these two are extremely close at 0.0152, and this is 0.0154. So you're talking it's a 0.0002 difference between the two. All right. So again, that kind of shows you that their little simulations came up with standard deviations very close to what our theoretical would have given us. All right. And in fact, as the sample size gets larger, we see the difference between the two numbers get smaller and smaller and smaller. All right. C, looking at the histogram in example 1, what sample size would you be comfortable using the normal model as an approximation for the sampling distribution? So in this case, it's saying, hey, if we look at these four graphs, which one of them would have been the first one you would have been okay with using the normal model? Now, if I were a betting man and had to pick which one would be first, this is obviously skewed right. I don't want to use this. And again, this one's pretty skewed right as well. As you can see it tapering off here, but not so much on this side. So I would probably say sample size of 100 is the first one I would have felt comfortable. It still isn't perfect. It's not as good as this one because we talked about the curves before. But this one, I'm probably like visually, I feel okay about it. So I would say sample size of 100 is the first one where I really feel like it would have been possible to use the normal model. Now it says in D, what does the success failure condition say about the choice you made in part C? This is, if you remember, what is the success fail condition? Success fail condition is that n times p and n times q must both be bigger than or equal to 10. All right. That is the success fail condition. So if I look at what we just chose, all right, as our thing, I said the 100 seemed like the reasonable sample size to use. So if we follow this and go, we would say n's 100. So I do 100 times p, which remember is 0.05. So what is 100 times 0.05? It actually turns out being 5, which means if we chose the 100, then that means that we actually would have failed the success failure condition. So we wouldn't have been able to use that model because it would have failed the success failure condition that says n times p must be bigger than or equal to 10. It actually is only bigger than or equal to 5. Now, if you look at the next sample size we had of the 200, you can see in this case we would be able to say 200 times 0.05 does give us 10. So that would pass that condition. All right, let's go ahead and take a look at our next question. Okay, this one says that the candy company claims that 16% of milk chocolate M&Ms it produces are green. Suppose that the candies are thoroughly mixed and then packaged in the small bags containing about 50 M&Ms. A class of elementary school students learning about the percents opened several bags, counts the various colors of candies, and calculate the proportions that are green. If we plot a histogram showing the proportions of green candies in the various bags, what shape would you expect it to have? So I started kind of drawing a histogram down here, and it says here that we expect 16% to be green. Now, obviously, it's not going to be 16% every time. The sample size is 50 here, so not super large, but at the same time, a decent size, sample size being decently large, all right? So we would go ahead and look. Now, what would I expect this to be? Would I expect many of my bags to only have somewhere between 0 and 10%? Actually, probably, yeah. 10% is pretty close to 16. It's not perfect, but I bet you there would be a decent amount that would fall in that range. All right. Now, what percent of the bags do I expect, or sorry, not what percent, but how many of them do I expect to be between the 10 and 20% range? Well, considering it's supposed to be 16, and 16 falls almost right in the middle of the range, that would probably be our highest bar for this distribution, because we would expect most of them to fall in that range. All right. Now, as we get away from there, we would start to see this kind of decline happen where we won't really see too many of the other ones. And it would be really rare to have some all the way out here. All right. But it could happen since our sample size is only 50. But for the most part, we would expect most of our answers to stay up in this range. Okay. So this is kind of what I would expect it to look like. So if it says what shape would I expect it to have, I would define this as being skewed right. So I think that this should have a skew right. Now, part B says, can this histogram be approximated by a normal model? Well, considering we just said it should be skewed right, probably not. But why? Well, it should be able to be normal by the central limit theorem. But the problem is we actually have not checked our conditions yet. So if I go back through and check our conditions, again, it says that they were thoroughly mixed and packaged, so we probably meet the randomization condition. 50 is a reasonable size for sample, all right? So when we're looking through our conditions, it hits most of them. We would not think 50 would be 10% of all M&Ms out there because, let's be honest, there's an unbelievable amount of M&Ms in the world, so that wouldn't be an issue. The only one we would have to check is, again, that success-fail condition that says that n times p must be greater than or equal to 10. In this case, n would be 50, and our p is 0.16. If we multiply that out, we're going to find out that that is actually equal to 8, which means we fail the success-fail condition, which means can this histogram be approximated by a normal model? No, because it would fail the success-fail condition, all right? Now, at the same time, we should be able to have a a decent understanding of it. It should be close to a normal model, but because we fail that condition, it's not going to be perfect. Now, let's say it were perfect. Where should the center of the histogram be? Well, we know that the center of a histogram of a sampling distribution should just be whatever your original proportion of success is. So in this case, C, where should the center be? It should be at 0.16. Now, where should the standard deviation be? Well, remember, we would be again following our little formula here that we would want to do p times q divided by n, and then take the square root of the whole thing. So we're looking at 0.16 times 0.84 divided by 50, and then taking the square root of that entire answer. Now I'm going to plug that in right now. I got 0.16 times 0.84 divided by 50, and then take the square root of that whole thing, and it's going to give me 0.051846. All right. So that's what we would expect the standard deviation of this sampling distribution to be. All right. So when we're looking at this question, not too difficult. It's really kind of just asking us if we know how to check the conditions, and it's asking us if we understand what the whole central limit theorem says about where our center and standard deviation should be. All right. Hey, are you guys still paying attention? Fine. We'll go ahead and stop here for this video, and we will pick back up on the next video. So I hope you found some of these questions to be useful. I hope you were able to do some of them on your own before I went through them with you. And as always, guys, stay fit, stay healthy, and have a wonderful